An ionic compound forms when electrons are transferred and the resulting oppositely charged ions attract one another. And this just doesn't happen once, it happens over and over and over. You get a whole array of positives surrounded by negatives and vice versa. This is an ionic lattice. It would look something like this. You'd have all your NAs surrounded by CLs. You'd have all your CLs surrounded by NAs, on and on and on, in 3D. Like that. That's a lattice. When we write the formula for an ionic compound, we're writing the lowest ratio of the ions in the lattice. But first, atoms have to become ions. They do this by gaining or losing electrons. For example, Mg always becomes Mg2+. How many protons does an atom of Mg have? When you look it up on the periodic table, it's 12 protons. How many electrons does an Mg atom have? That must also be 12 for it to be a neutral atom. So what happens to make an atom of Mg become an Mg ion? As a reminder, what is it that makes a particle magnesium at all? It's the number of protons, which is the atomic number. That number cannot change, or it's no longer magnesium. So magnesium can't gain or lose protons. Like it says above, atoms become ions by gaining or losing electrons. So Mg can gain or lose negative electrons. How then does Mg change from neutral to +2? The Mg ion has to have 2 more positive particles than it has negative particles to be a +2 object. The number of positive protons can't change, so Mg has to lose 2 negative electrons. Putting all that together, how many protons does the Mg ion have? It has 12 protons. How many electrons does it have? That's where the change is. It's now 10 electrons to make a magnesium ion. What about our second example of fluorine? A fluorine atom and the fluoride ion must have 9 protons, otherwise it's no longer fluorine. The difference is how many electrons. A fluorine atom has the same number of electrons as protons, so 9. When F becomes a -1 ion, it has to change the number of electrons. So this time it gains 1 negative electron to become a -1 ion. Remember that the representative elements always obtain the same charge when they ionize. Make sure you remember which elements are the representative elements. That's everything in column 1, everything in column 2, everything to the right of the stair step, as well as the element aluminum. You have to be able to tell the charge of these elements entirely based on their location on the periodic table. The elements in column 1 always become +1 ions, column 2 +2, column 3 +3. Remember that we skip column 4. These are the elements that are kind of at the in-between in terms of how many valence electrons they have, so they don't often bond ionically, so we just skip that column. The representative elements in column 5, then you're going on the negative side. So column 5 are your -3 ions, column 6 -2, column 7 -1, and again we skip column 8 because those are your noble gases. They don't make ions, they don't bond in any way. When a metal and a nonmetal bond, Na and S for example, they first become ions. Na becomes a +1, S becomes a -2. The magnitude of each charge determines how these two specific ions can interact. There's only one ratio that results in an electrically neutral compound. There's only one possible formula between Na and S. There must be 2 Nas for every S for the charges to cancel. So we always get the formula Na2S. Because there's only one possible formula between 2 ions, prefixes are not needed in names of ionic compounds. Now when it comes to writing formulas, remember you learned a shortcut in Chem 1. You learned about crisscrossing. You look at those charges, particularly the number of the charge. Na with a plus sign, of course, means it's Na plus 1. You take those numbers and you cross them over and down. You take the 1 here, and it's going to become the subscript on the S. You take the 2 here, it's going to become the subscript on the Na. And that's the little shortcut technique for writing these formulas, for getting that formula Na2S, for example. The rules then for writing ionic formulas are, always write the cation first. Formulas do not contain charges. These charges were used to determine the subscripts, so the charges are gone. Ionic formulas will contain subscripts, and that includes understood ones. We don't write the 1, but it's understood to be there. The end formula should always be electrically neutral, and you always write the lowest possible ratio. Try writing formulas for these compounds. These contain only representative elements, so first look up the charge of each ion. Crisscross these charges to get the correct formula. For example, magnesium chloride. When you look up magnesium, you see it's in column 2, so you know it's a +2 ion. Chlorine, when you look it up, is a -1 ion. You take the numbers and you crisscross them. So the 2 goes on the chlorine, the 1 is the subscript of magnesium, and the formula becomes MgCl2. The next example, aluminum oxide. Al is a +3, O is a -2. Crisscrossing these charges and making them subscripts gives you the formula Al2O3. Sodium and iodine, those are both 1 ions, so the formula is only NaI. Calcium oxide, Ca and O, are both 2 ions, but we don't write Ca2O2. Remember that for ionic compounds, we always reduce to the lowest possible ratio, so we reduce this to simply CaO. Potassium sulfide is K2S, and lithium fluoride is LiF. Of course, you have to go the other way too. Here are the rules for writing ionic compound names. Again, cations come first. Do not use prefixes. They're no longer needed because the ions of specific charges can only combine in 1 possible ratio. And we use the IDE ending when the anion is a monatomic ion. That means the anion is the ion of a nonmetal on the periodic table. It's not a polyatomic ion. Try naming these examples. These are straightforward. You only need the names and the IDE endings right now. So VeO becomes beryllium oxide. MgBr2, remember, we don't have to explain the 2 in the name. It would be figured out knowing the charges of these ions. The name for MgBr2 is just magnesium bromide. K2S, potassium sulfide. Li3P, lithium phosphide. Now we need to add transition metals to the mix. Unlike the representative metals, the charge of a transition metal cannot be determined based on the metal's position on the periodic table. Transition metals are all those metals located in the B columns on the periodic table. Everything in here. And remember that this section is actually within the transition metal section here. Additionally, these metals over here in this little triangle that are sometimes called the other metals, those can also have variable charges. So really we're referring to all the metals that are not the representative metals. Those can all have multiple charges under different conditions. There are a few metals in this section, though, that do not have multiple possible charges, and you will need to memorize these. Ag is always +1. Zinc and cadmium are always +2 ions. Make sure and get those memorized. In one of two ways, the charge of a transition metal has to be given as part of the compound's name. The most common and easier way is the stock system. The charge of the transition metal is given as a Roman numeral after the metal name. An older system that's still sometimes used is the classical system. Here, the suffix OUS on the name of the metal refers to the lower of the two possible charges, and the suffix IC refers to the higher of the two possible charges. This system isn't as user-friendly. It doesn't explicitly tell you the charge. You have to have those memorized. Also, some of the metals revert back to their Latin name. So, for example, if you saw cuprous, that's copper, the Latin name, and you would have to have memorized that copper can be a +1 or a +2, and OUS being the lower, that means copper +1. You have a list of common transition metal charges on your summer memorization list. Start memorizing them. At the very least, make sure you know copper and lead and iron. But notice, a lot of the transition metals have +2 and +3 as their two common charges. So you might want to memorize those and then fill in the couple others that are different. Try these examples. Write the formulas for these three names that are given. The thing to remember here is that the Roman numeral means the charge on the transition metal. So for this first example, that Roman numeral 2 means we're dealing with a Pb +2 ion. Chloride, of course, that's a representative element, so you can look that one up on the periodic table. That's Cl-1. When you crisscross these charges, like you always do for ionic compounds, the 2 goes on the chlorine. The 1 is an understood subscript for the lead, so we get PbCl2. Doing the same thing for copper 1 sulfide. You're dealing with copper with a +1 charge, sulfur with a -2 charge. Crisscrossing, that gives you Cu2S. For this last one, they give you the transition metal name using that classical system, so you have to do a little translating. Ferric, this refers to the element iron, and the IC ending means it's the higher of the possible charges for iron, and in this case, that's a +3. You're putting that with oxide, O, with a -2 charge. Crisscrossing these then gives you Fe2O3. Some students have a little more trouble going this other direction. Given the formula, you have to write the name. You have to remember to figure out the charge of the transition metal and include it as a Roman numeral. One way to figure out the metal's charge is by uncrossing. We crisscross charges to get subscripts before. Now we'll uncross subscripts to figure out charges. In this example, nickel has an understood 1 subscript. So crossing that back up suggests that bromine here is a -1 ion. Doing the same thing with the 2 on the bromine suggests that nickel here is a +2. Always check to see if the anion charge is correct. Is Br really a -1 ion? Yes, it always is. It's a representative element. It always has that same charge. If the anion charge is correct, then the transition metal charge is correct too. So NiBr2 is nickel 2 bromide. Uncrossing the second example, the subscript of 2 becomes the charge of oxygen. The subscript of 3 becomes the charge of chromium. Oxygen really is a -2 ion, so this chromium really is a +3 ion, meaning the name is chromium 3 oxide. On the last one here, when we uncross, it suggests to us that our Pb is a +2 ion from this subscript of oxygen, and from the understood 1 on the lead, it says that our oxygen should be a -1 ion. Of course, oxygen isn't ever a -1 ion. Oxygen is always a -2. So for this charge to be right, it would have to be doubled. That means for the charge of lead to be correct, it also needs to be doubled from what we currently have. Lead in this compound is not a +2, it's actually a +4. The correct name for PbO2 is lead 4 oxide. With uncrossing this way, that is the only thing you have to watch out for. Check the anion charge and see if it is correct. And if it's not, you have to double it, like in this example, then you have to double the charge on your metal before you report it.